Welcome to The Explainer. Today, we're diving deep into the hidden geometry of neural networks. Why? To solve a paradox that has puzzled researchers for years. And it all kicks off with a rule of thumb that, as you're about to see, might be a complete illusion. So let's get right into it. If you've been in deep learning for any amount of time, you've heard this one, right? To get a model that actually generalizes, performs well on data it's never seen before, you need to find a solution that's sitting in a nice, wide, flat valley in the loss landscape. The thinking goes, flat minima, good, sharp minima, bad. Sounds simple enough. But here's the kicker. What if I told you that this whole idea of flatness is basically an illusion? I mean, look at this. You can have two totally different views. One looks super flat, the other looks incredibly sharp, but they are describing the exact same model solution. This isn't a trick. This was the core finding of a paper back in 2017 that just blew up our whole understanding of how generalization works. So what's going on here? Well, it turns out there's this little mathematical trick. It's called reparametrization, and it lets you take any flat minimum and make it look sharp. And you can take any sharp one and make it look flat. But here's the most important part. This doesn't change what the model is actually doing at all. It's the same function, the same predictions. We're just describing it with different numbers. And this creates a massive problem, right? Think about it. If our way of measuring flatness is so flimsy that it can change just because we decided to describe the model a little differently, how on earth can it be connected to something as real and fundamental as generalization? I mean, how well a model performs isn't arbitrary. So if our metric is, the whole theory just falls apart. Okay, so to really get what's happening, we need to completely change how we think about the space our models live in. An analogy might help here. Imagine the true parameter space of your neural network is the Earth. It's a globe, right? It's curved. And the real distance, say between New York and London, is a fixed physical thing. It is what it is. It's an intrinsic property of the globe. It doesn't just change. Okay, so if the network is the Earth, then our mathematical description of it, the actual weight values we write down, that's like a flat 2D map of the globe. And we all know what happens with flat maps, right? A Mercator projection makes Greenland look absolutely massive, way bigger than it really is. Different map projections distort the planet in different ways. It's the same Earth, but we're getting these totally different warped views of it. And that right there, the act of choosing a different map projection, is exactly what researchers call reparametrization. It's nothing more than picking a different coordinate system to describe the same underlying thing. So that illusion we saw earlier, the flatness or the sharpness, it's not a real property of the model. It's just a distortion, an artifact of the specific map we chose to look at it with. Okay, so if all our standard maps are giving us a distorted picture, how do we get to see the real thing, the true undistorted landscape? Well, lucky for us, the answer comes from a field of mathematics that was literally designed for this exact problem, how to deal with curved spaces. It's called Riemannian geometry. And this field gives us this amazing tool called the Riemannian metric. You can think of it like a universal measuring stick. It's a way to measure things like distance and curvature directly on the globe, not on our wonky, distorted, flat maps. So no matter which map projection you use, the metric tells you the truth about the underlying geometry. And this is where it all comes together. When we start using this metric in our calculations, we can suddenly measure things that are invariant. And what that means is we can find properties that stay the same no matter how we reparameterize the model, no matter which map we use. We can finally get a true, consistent measure of flatness. We can see optimization paths that don't change arbitrarily. We get a view of the landscape that is totally independent of our coordinate system. All right, so with this powerful new geometric lens, let's go back to those problems we started with and see how they just melt away. Okay, check this out. The research here is so elegant. Once you account for the geometry, all those weird inconsistencies, they just disappear. For flatness, for example, we stop using the standard Hessian matrix. That's our old, unreliable tool for measuring curvature. Instead, we use this new metric-aware operator that gives us a result that is invariant, a result we can actually trust. And for optimization, it turns out that any gradient descent path is actually consistent. The trick is, you have to look at it through the right geometric lens. It's not that some optimizers are weird and some aren't. It's that we were ignoring the geometry of the space they were moving through. Okay, this is all fascinating theory, but what about the real world? How does this new perspective change how we think about the stuff we actually do every day, like, say, weight decay? Yeah, what does weight decay really do? It's a great question. And to answer it, there was this really interesting debate that popped up on Reddit, which perfectly captures the old way of thinking versus this new geometric view. So, first up, you've got the classic textbook answer. A Reddit user, I'm a Sokowans, summed it up perfectly. They said weight decay is a regularizer. Plain and simple, it's there to penalize large weights, stop the model from getting too complex, and prevent overfitting. I mean, that's what I was taught, and probably what you were taught too. But then, one of the authors of the actual paper we're discussing jumps into the thread. And they offer a totally different take, one that fits perfectly with this new geometric picture. They argue that weight decay's real job, it's not regularization, not in the old school sense anyway. It's something much deeper. It actually changes the dynamics of training. And this is the mind-blowing part. The key insight is this. Weight decay isn't just about shrinking weights on some fixed, static landscape. No, it is actively reshaping the geometry of that landscape while the optimizer is trying to navigate it. It's changing the curvature, it's changing the terrain, and that fundamentally alters the path the model takes to find a solution. So all of this really brings us to a fundamentally new way of seeing deep learning. It's a huge shift in perspective, right? We're moving away from thinking about things in a flat, simple, grid-like world to seeing it for what it is, a vast, rich, curved geometric space.
So if there's one thing to take away from all this, it's that so many of the weird results and paradoxes in deep learning pop up for one simple reason. We're trying to use a flat map to navigate a curved world. It just doesn't work. But once we embrace the true geometry of the space, once we start using the right tools for the job, like the Riemannian metric, we get a much deeper, more unified, and honestly more sensible understanding of how these incredible models actually work.
And that leaves us with one final, kind of provocative thought to chew on. If something as basic as flat minima are good turned out to be just a geometric illusion, what other truths that we hold about deep learning are also just distortions? What other fundamental ideas are just shadows on the cave wall, created by our limited flat map perspective?